So now moving on to our Module 12.2, our second section for Module 12, we're going to be taking a look now at external convection, specifically looking at the flow over bluff objects. So within this section here, we're going to cover the topics of the cylinder and cross flow, looking specifically at the flow considerations and convection, heat, and mass transfer. Then we're going to look at our sphere, move along to our flow across a bank of tubes, talk about our impinging jets, looking at our hydrodynamic and geometric considerations, as well as our convection, heat, and mass transfer. And last, we'll finish up with packed beds. So within this module here, our 12.2, again, we're going to go over the theory for these above topics, talk about our governing equations, look at some practical applications, and then go through my hand solution to an example problem. So as we continue on with our Module 12.2, we're going to be taking a look at external convection, the flow over bluff objects for cylinders, spheres, and packed beds. This relates back to Chapter 7 in our textbook, specifically sections 7.4 through 7.8. So let's take a look at the cylinder and cross flow. So conditions are going to depend upon the special features of the boundary layer development, including onset at the stagnation point and separation, as well as transition to turbulence. So looking at these terms on our diagram below, we can see there's our velocity coming in here. This is our stagnation point. So our forward stagnation point is right here. And this is right at that boundary layer. So we can see that boundary layer going there. And off over to the right here, we see our separation point where it actually starts to separate there, where it transitions to turbulence. So that now leads to the question of what is our stagnation point? Well, our stagnation point is going to be the location of our zero velocity. Our use of infinity is equal to 0, and we have a max pressure. So at this stagnation point here, we know that we have our velocity equal to 0 and a maximum pressure right at that point. Now this is going to be followed by the boundary layer development under a favorable pressure gradient where our dp over dx is going to be less than 0. Hence acceleration of the free stream flow, or our du infinity, our change in our velocity relative to our position x, needs to be greater than 0. So du infinity over dx is greater than 0. Now, one thing that we want to note here is that as the rear of the cylinder is approached, the pressure must begin to increase. Hence, there's going to be a minimum in the pressure distribution, our P of x for pressure distribution, after which boundary layer development occurs under the influence of an adverse pressure gradient. So we have the relationship that we see here, that our derivative of pressure with respect to position, dp dx, is going to be greater than 0, and the derivative of velocity relative to position, our du infinity dx, is going to be less than 0. So now I want to take a minute and talk about separation. When does separation occur? Well, separation is going to occur when our velocity gradient reduces to 0, where our velocity gradient is shown as a relationship of du over dy, which is evaluated when y is equal to 0. So our change in u with respect to y when y is equal to 0. And this is going to be accompanied by a flow reversal. So we can come up to our diagram here and we can see this is where our flow reversal occurs, and a downstream wake. So after this here, we can see our downstream wake, and this is our separation point right here. Again, this occurs when our velocity gradient reduces to 0. Now, often the question is, where does this occur? Well, the location of the separation is going to be dependent upon the boundary layer transition. So we can come down to our diagram, see there's our laminar boundary layer, and we can see our separation occurring right there. Where is the location of separation? Well, this is going to depend upon these boundary layer transitions. So we can see our transition is located right here. And this is where it turns into our turbulent boundary layer. You see the turbulence occurs right there. And this is going to be based upon our Reynolds number. So we have our Reynolds number Re sub d, and this is equal to our rho Vd over mu, which we can reduce down by our relationships we've seen previously within this course and within this chapter to Vd over nu. Where in this Reynolds number relationship, we see that our rho is our mass density, so there's our rho there. Our v is our fluid velocity. Our d is the diameter of our cylinder, and our mu here is our viscosity. So again, we can replace this based upon relationships we've seen before. We now have Vd over nu, where V, again, is that fluid velocity, d is still the diameter, and now nu here is going to be our kinematic viscosity. So now I want to take a look at this force imposed by the flow. Now this is going to be due to a combination of the friction and drag form. So there's going to be two components to this force, one of which is going to be due to the boundary layer surface shear stress, or our friction drag, which is we mentioned right here, and the other component is going to be due to a pressure differential in the flow direction resulting from the formation of a wake. So it's going to be form, pressure, or our drag. So this is going to be our form drag right here. And then from this, a dimensionless drag coefficient, our C sub D, can be defined by this following relationship. So C sub D is equal to, you see on our numerator here, F sub D, where F sub D is our drag force. And this is going to be divided by our A sub F, where A sub F is the cylinder frontal area, times now our rho V squared over 2, where rho is our mass density and V is our fluid velocity. So this AF, or the cylinder frontal area that we discussed in this relationship, this is going to be the area projected perpendicular to the free stream velocity. So the thing we want to note about our drag coefficient, our C sub D, is that this is going to be a function of Reynolds number. And the results from this can be displayed below in this figure. So we can see on our x-axis, we have our Reynolds number. And on our y-axis, we have our C sub D, which again is our drag coefficient. So we can see there's a function of each other. And what this figure shows are the drag coefficients for a smooth circular cylinder in Clausius as well as a sphere. So we can see this curve here shows the results for a smooth cylinder, and this curve here shows our results for a sphere. Now we can note there's a relationship between our CD and our Reynolds number shown here by this dotted line. And we look up top here in this region here, for a Reynolds number up to that value at this line, there's no separation. Then we go in for our separation at 80 degrees, and we pass this line over here, and we're at 140 degrees. So next we want to take a look at these heat transfer considerations. So first let's take a look at our local Nusselt number. So a couple of questions we can ask ourselves about this. So how does the local Nusselt number vary with our theta for a Reynolds number that's less than 2 times 10 to the 5th? And what conditions are associated with the maxima and minima in the variation? Then we can also ask ourselves the question of how does a local Nusselt number vary with theta for a Reynolds number greater than our 2 times 10 to the 5th, and what considerations are associated with the max and min in that variation? So to answer that question, we reference back to our textbook here, and we can see that, well, if our Reynolds number is going to be less than or equal to 2 times 10 to the 5th, then the boundary layer remains laminar, and the separation occurs when our theta is equal to 80 degrees. And we can reference back to figure 7.8 in our textbook. However, if our Reynolds number is going to be greater than 2 times 10 to the 5th, then our boundary layer transition occurs and separation is delayed to our theta is equal to 140 degrees. So again, we just saw that in the figure. So that kind of answers our questions in relationship to our local Nusselt number. So rather than looking at our local Nusselt number, what if we want to take a look at our average Nusselt number? So we have this relationship that we see here, that we have our average Nusselt number is equal to our h bar times our diameter d divided by our thermal conductivity k. So for this here, we can now take a look at this correlation below, given by equation 7.54 in our textbook. This is the Churchill and Bernstein correlation. So we can see here a relationship now for that average Nusselt number given by this large expression from equation 7.54. So we can see this is going to be dependent upon our Reynolds number, our PR number, and those are really the only two things that we need to plug into this relationship in order to get this average Nusselt number. So I would suggest going back to this section in your book, looking at this equation 7.54 and seeing the derivation of this expression for this correlation, for the Churchill and Bernstein correlation. Now we also have the case here, if we're dealing with cylinders of a non-circular cross-section, then we have these two relationships that we see here. And I've referenced you back to your table 7.3 for the values for your C and M that you plug in for this average Nusselt number. So this is in order to calculate the average Nusselt number for cylinders of non-circular cross-sections. So now I want to discuss the topic of flow across tube banks. So what are some common applications where this could be used for? Well, we see these tube banks commonly for different types of two-fluid heat exchangers. So this is a common geometry that you'll see within those. And within this, there's two different types of geometry we'll discuss. We're going to discuss aligned and staggered arrays. So either type of these, what we can see though, is you have this fluid in cross flow over the bank, the tube bank. So you can see cross flow, this means that this is going to be running perpendicular to the tube bank where you have the internal flow of the fluid that's running through the tube that's going to be perpendicular to that there. So this is going to be, again, common for our two fluid heat exchangers. So now let's talk about these different types of arrangements. So you can either have aligned or staggered arrays. So if we're dealing with an aligned array, we have the situation that we see on the left-hand side of our diagram where this is our S sub L and our S sub T, everything's symmetric, and these are aligned together. We have our diameter of our tube right there as D. So based upon this, for a line, we have the following relationship that our V max is going to be equal to our ST, which is our distance between these two, on-center distance between those within this aligned array. And this is going to be divided by ST minus D, where D is the diameter of the tube, times our V, when there's our V right there. Now, if we have staggered, we have two different relationships. So these relationships are going to be based upon the distances SL and SD and how they relate to each other. So if we're looking at a staggered array in part B, we have the following relationship that V max is going to be equal to our ST, and now we can see our ST is still this distance right here on center, divided by ST minus D, where D is still the diameter of the tube, times our V. Now if, this is for the case now, if 2 times our SD right here minus the diameter D is going to be greater than ST minus D. So that's the case, then we use this relationship here for our V max. So we can see that this is the same relationship we have for aligned. So for staggered, it will be that same relationship for our V max as we saw for aligned if this is the condition met here between the relationship between our ST and our SDs. So the other situation is when 2 times SD minus our diameter D is less than or equal to our ST minus D. Then this changes here, and you can see how this changes is now we see this 2 in the denominator down here. So this for our V max is now going to be equal to that ST distance right there divided by 2 times our SD distance minus our diameter D times that velocity V. So now let's take a look at the flow conditions for both the arrangements being aligned that we see over here on the left for our tube banks and our staggered array for our tube banks that we see over here on the right, and how this affects the flow conditions within each of these. So we can see where it becomes turbulent. We can see our preferred flow lines within this here, and we can clearly see that each of these tubes within this is perfectly aligned in the diagram on the left, and on the right we can see the staggered configuration for the staggered array of tube banks. So the thing to really notice within these diagrams here as we talk about these preferred flow lines, so you can see these preferred flow lines as they're going right through here, when they're not staggered and they are aligned, it does give you that path to go through for these preferred flow lines. Whereas we do have, when we have the staggered array over here on the right, you really don't see that. It's still got to kind of follow around each of those cylinders within the bank. Now, typically what we want to know and calculate is the average heat transfer coefficient for the entire tube bank. So we do have a correlation that we can see down here in our equations 758 and 759 for our average Nusselt number for an isothermal array. So we come down into this equation here, and we can see that our average Nusselt number is going to be equal to this variable C2 times, now in parentheses here, our C1 times our Reynolds number for this relationship here for our Reynolds number, times our PR to the 0.36, times now our PR over our PRS to the 1/4. Now the question here is, well, what do we put in for our C1 and our C2? And this is where we can go to our table 7.5 and 7.6 that we'll look at on the next slide to get our values for C1 and C2 to plug in to solve for our average Nusselt number for this isothermal array. Now another thing to note within this relationship here is that all properties are going to be evaluated at our initial temperature plus our TO divided by 2, except for our PRS, which is going to be evaluated just at our surface temperature, our TS. So now here are these two tables to solve for our C1 and our C2 that we need for those equations 7.58 and 7.59 that we just looked on the previous slide. So table 7.5 is how we can solve for our C1 and our M values, and this is the constants that we need for this tube bank. So we can look over here, well, what configuration is our tube bank? Well, is it aligned or is it staggered? And then we can look at, well, what is our Reynolds number, our max Reynolds number here? Based upon that, whether it's aligned or staggered, we can then find our value for C1 and our value for M. Now, with any tables, you should always look down to any of the footnotes below. So for this one here, it tells us that for the value of our ST over our SL, if this is less than 0.7, the heat transfer is inefficient and aligned tubes should not be used. So that's always a good thing to do, is take a look at these footnotes and any subnotes that we have for the tables that we're using. So then moving on to our table 7.6, this is the correction factor, C2 for that equation 7.59, for our N sub L less than 20. So again, pay attention to these notes right here to use this here. So we can see, are we aligned and are we staggered right here? And based on that, we can then get our values for our C2. And these values for C2 are going to be based off of this relationship for our NL. And you see this is less than 20. This goes up 1, 2, 3, 4, 5, 7, 10, 13, and 16. So these are less than 20 to utilize this to find that correction factor C2 from this table 7.6. So now let's take a look at this T sub O, or our fluid outlet temperature. So we can define this in a relationship shown below, where we have on our numerator here our surface temperature minus our fluid outlet temperature, Ts minus To, all divided by our surface temperature minus our initial temperature, Ts minus T infinity, is equal to e to the negative. Now we can see over here on the numerator we have pi d n times our h bar, all divided by rho v nt times st times our C sub p, where our n is going to be the total number of tubes in the bank, our n sub t is the total number of tubes in each row, and our C sub p is going to be our specific heat at a constant pressure as we plug into this relationship here. And for our n, this total number of tubes, this is going to be equal to nt times our nl, and that'll give us that total number of tubes. So now taking a look at our total heat rate relationship, we can see that our Q is equal to our H bar times AS times our delta T, where our AS is given by this following relationship here based on the dimensions of our object. So this is going to be N, where N is the total number of our tubes, times pi dl. So diameter and our length. That's where we get our A sub S from to plug back into our equation for Q here. And what is our delta TLM? Well, delta TLM down here is given by this relationship here, where we have our TS minus our TI minus, now our TS minus our TO, where TO is our fluid outlet temperature. And this is all divided by the natural log of our ratio of our temperature differential here of TS minus TI all over our TS minus our TO. Now if we take a look at our pressure drop, we can see we have the relationship shown in equation 7.65 in our textbook, which is that our delta P is equal to our NL times now this correction factor times, we see this relationship here where we have our rho V squared, V max squared all over 2 times F, where F is our friction factor. Now our X and our F we can see on the following slides in figures 7.14 and 7.15 as we relate back to our textbook. So now let's take a look at our figure 7.14. In this figure here, we have our friction factor and our correction factor. We can see our friction factor over on our y-axis, and we can see our correction factor here on this small graph inside of our larger graph. Now these relate back to our equation 7.65 that we looked at earlier, and I've included down below here. And this is for an inline two-bundle arrangement. So again, this particular 7.14 is for the aligned one. So now let's take a look at figure 7.15. So this is for the staggered tube bundle arrangement rather than the aligned. So we can see that configuration up here. We again see on our y-axis we have our friction factor F, and over here we have our correction factor. And these again relate back down once we get these values from these figures to our equation 7.65 in our textbook that I've wrote out down below here as well. So now I want to take a look at the topic of the sphere and packed beds. Now if we're talking about the sphere, let's discuss the flow over a rigid sphere. So our boundary layer development for this is going to be very similar to that we've seen before in the flow over a cylinder. And it's going to be involving our transition and separation. Now we have our governing equation for our average Nusselt number shown here by equation 7.56 in our textbook. This is going to involve our Reynolds number and our PR number, as well as our mu and our mu sub s. Now for our Reynolds number, we do have a relationship between our drag coefficient, our CD, and our Reynolds number, and this is shown in that figure 7.9 that I have over here small to the right, but we've looked at that earlier within this module as well, where you have your Reynolds number on the bottom. You can see our relationship here based on our curves here between our CD and our Reynolds number, and we can see our CD, our drag coefficient, on our y-axis as well. And recall, this was for both a smooth cylinder and a sphere, so now we're dealing with a sphere, so we can go back to that figure 7.9 to again get that relationship between our drag coefficient and our Reynolds number. So now let's move along to the topic of packed beds. So in particular, let's take a look at gas flow through a packed bed. And that's what we have in this figure here. We can see our packed bed in the center. We can see our flow moving at a velocity v. Now this flow is going to be characterized by curvilinear paths through a bed of fixed particles. Now this large surface area per unit volume renders configuration desirable for the transfer and storage of thermal energy. So looking at this idea of gas flow through these packed beds of solid particles, this is going to be relevant to a lot of different industrial processes. Some of these processes include the transfer and storage of thermal energy, heterogeneous catalytic reactions, and drying. So this term packed bed refers to a condition for which the position of particles is going to be fixed. So in contrast, a fluidized bed is one for which the particles are in motion due to advection within the fluid. Now for these packed beds, a large amount of the heat and mass transfer surface area can be obtained in a small volume due to the nature of what they are. And the irregular flow that exists in the voids of the bed enhances transport through mixing. So we do have some governing equations related to our packed bed of spheres. The first equation we'll take a look at is 7.81. So within this we have our void fraction of porosity, our epsilon value, times our JH average, which is our Colburn factors defined by, back in chapter 6, our equation 6.70 and 6.71. And this is equal to 2.06 times our Reynolds number to the negative 0.575. And we do have relationships that we can plug in to solve for our Reynolds number as well. Now, what is our void fraction, our porosity? Our epsilon here is going to be in the range from 0.3 to 0.5 for our epsilon value. Now, we also have this relationship down here for Q. The Q is equal to our H bar times our A sub P comma T times our delta TL, which we've already defined this earlier within our lecture here for a relationship for that. So what is our A of sub P comma T? Well, this is the total surface area of our particles that we can plug in there. And last, we have this relationship down here. We can see our temperature difference ratio here between TS minus TO, which again, we now have a relationship for our TO, divided by TS minus TI is equal to E to the negative, and we've seen this equation before, H bar times now this APT is the difference here, and we plug in that total surface area of the particles, all divided by our rho V A sub CB times our C sub P. We're getting this A sub CB, if we see on the bottom here, is now the cross-sectional area of the bed. So now let's use some of these key concepts, equations, and theories that we've looked at within this module and apply them to an example problem. So we're going to do this for example problem 7.72. So I'm going to go through my hand solution to this problem. Let's take a look at problem 7.72. In this problem, it tells us that they're in an extrusion process. Copper wire emerges from an extruder at a velocity given to us as V sub E and is cooled by convection heat transfer to air in cross flow over the wire, as well as by radiation to the surroundings. So now they show us the diagram down here. We have our extruder, and we have our wire coming out of it here. We have our position X from the base at the edge of the extruder going along the length of the wire. We have our air, all the properties associated with the wire here, and our surrounding. Now there's three different parts to the problem here. In part A, they tell us that by applying conservation of energy to a differential control surface of length dx, which either moves with the wire or is stationary and through which the wire passes, they want us to derive a differential equation that governs the temperature distribution T of x along the wire. In the derivation, the effect of axial conduction along the wire may be neglected, just letting us know that we can neglect that, and express your results in terms of velocity, diameter, and properties of the wire, which we can see here by these variables, and we can reference back up to our diagram as well. The convection coefficient associated with the cross flow, our H bar here, and the environmental temperatures T sub infinity and T sub surround. So these are the variables that we're going to be using to express our results. So that's part A. In part B, they tell us now we need to neglect radiation. So we need to obtain a closed form solution to the foregoing equation where they give us for velocity V sub E is equal to 0.2 meters per second, our diameter big D is equal to 5 millimeters, V is equal to 5 meters per second, and T sub infinity is 25 degrees Celsius. And an initial wire temperature given to us is T sub I is equal to 600 degrees C. They want us to compute the temperature T sub 0 at the wire at x is equal to L is equal to 5 meters. Now they tell us that the density and specific heat of the copper are rho density is equal to 8,900 kilograms per meter cubed, and our specific heat C sub P is equal to 400 joules per kilogram times Kelvin. While properties of the air may be taken to be K value of K is equal to 0.037 watts per meters times Kelvin, and V is equal to 3 times 10 to the negative 5th meters squared per second, and our PR is equal to 0.69. So then lastly, in part C of our problem here, they say that accounting for the effects of radiation, so now we're including radiation, with our E given to us as 0.55 and the temperature of our surrounding given to us 25 degrees Celsius, numerically integrate the differential equation derived from our part A to determine the temperature of the wire at L is equal to 5 meters. And they ask us to explore the effects of VE and E on the temperature distribution along the wire.
So we were given quite a bit of information in our problem statement and initial diagram. So it's going to become important in this next step here to clearly understand what they've given us and what they're asking us to solve for and what assumptions we can make based upon what they tell us in the problem statement. So the first thing I really want to do with this is write down all the variables and how they relate to the problem here and any values that we know in units that we're going to use for this. So in the problem, we're given our V sub E. Now our V sub E is the velocity of the emerging copper wire, and it's given to us as 0.2 meters per second. Now they give us D sub X. Now this is the control surface length. They also tell us our temperature distribution in T of X. We have our capital D, which is the diameter of the wire, and that's given to us as 5 millimeters, which we can convert to meters as 0.005 meters. They give us our rho, which is our density, with a value of 8,900 kilograms per meter cubed. They tell us our specific heat, C sub P, is 400 joules per kilogram times Kelvin, and our emissivity, epsilon, is given to us as 0.55. They tell us our H bar, or our convection coefficient associated with the cross flow, and they also tell us now that we have our temperature of the surrounding area is 25 degrees Celsius, and our T sub infinity, our ambient temperature, is 25 degrees Celsius as well, and these are our environmental temperatures. Now what else do they give us in here? Well, they tell us that V is equal to 5 meters per second, T sub I is equal to 600 degrees Celsius, X is equal to L is equal to 5 meters, K is given to us as 0.037 watts per meters times Kelvin, where V is given to us as 3 times 10 to the negative 5th meters per second, meters squared per second, and our PR number is given to us as 0.69. Now with this, we need to find 3 different things. So let's simplify down what we saw in the problem statement and break it into exactly what they're looking us to solve for. In part A, they want us to find the differential equation for temperature distribution, T of X. So this differential equation would be the dt over dx. And then part B, they want us to find the exact solution with negligible radiation for the corresponding value of temperature at X is equal to L is equal to 5 meters. And part C, they want us to find the effective radiation, so now we're including radiation, on temperature of the wire, effective wire velocity, and emissivity on temperature distribution. So those are the 3 things we're looking for to solve the problem. And here's a great page to reference back to with all of our variables and the values that they give us. Now that we've had a chance to write down all of our givens and what they're asking us to solve for, the next thing we want to do is, from that information they give us in the problem statement, what assumptions are we going to make to solve this problem? So first thing we're going to assume is that there's negligible variation of the wire temperature in a radial direction. We're going to assume that there's negligible effect of axial conduction along the wire. There's constant properties, radiation exchange between small surfaces and large enclosure. We're going to assume that motion of the wire has a negligible effect on the convection coefficient. So V sub E is much less than V. So for our solution, we have some properties for copper and properties for air. So we're given the density for copper is 8,900 kilograms per meter cubed. Our specific heat is 400 joules per kilogram times Kelvin, and our emissivity is 0.55. For air, we have our K value of 0.037 watts per meters times Kelvin. V is equal to 3 times 10 to the negative 5th meters squared per second. PR number is 0.69. So for our solution, we can take and apply the conservation of energy to a stationary control surface. So our E dot in minus our E dot out is equal to 0. Our inflow due to advection here, transport due to bulk fluid motion. And our outflow, we have advection, conduction, and radiation. For the next part of our solution, we move to equations 5.1 and 5.2 on page 281 of our textbook. So we have our inflow and our outflow. So in our inflow here for advection, we have rho, V sub E, A sub C, C sub P, and T. Minus, for our outflow, we had another advection term here, where we have rho, VE, AC, CP, and now T plus DT. Then for our convection part, we have DQ convection, and minus our radiation, D sub Q radiation, is all equal to 0. So this is all utilizing equations 5.1 and 5.2 from our textbook for all the different parts that we're dealing with, advection, convection, and radiation, where our A sub c that we're seeing in this equation here is given to by the relationship of pi d squared over 4. So we can plug that back in for our A sub c to our equation from above here. So we rewrite our equation above here, plug in for our terms for A sub c, now with this relationship here, and this becomes this down here. And what we can see as we go through this is that certain parts of this will cancel out. So our t's will cancel there. We have negatives that will cancel out, double negatives, all that. We can reduce this down here a little bit more. And then what we can see is we do have a relationship for our Q convection and our Q radiation. So these two terms, if we go back to chapter 1 where we have equations 1.3 on page 8 and 1.7 on page 10 of our textbook, we have relationships for both of those for our convection and for conduction. So those can be plugged in up here to our equation now. So we can plug in these, 1.3 and 1.7, into the relationship we got from 5.1 and 5.2. So now we can plug in equations 1.3 and 1.7 for our convection and radiation terms. So we plug those into that above equation we just saw, and we end up with this relationship here. Now we have negative rho VE times our A sub c of pi d squared over 4 times our Cp times dt. This again our specific heat and our differential temperature, minus dA times our h bar value times the temperature difference between T minus T infinity, which is our convection term when we plug it in here. And then over here we have a dA epsilon sigma there times T to the 4th minus T surrounding to the 4th equals 0 for our radiation term. So that's when we plug in 1.3 and 1.7 for those terms there. Now we know that we have a dA here, where dA for our specific problem here is 2 pi r dx, or pi d dx, whether we're dealing with radius or diameter. They gave it to us in diameter, so we can switch back to that. Plug all that back in here, and we now end up with this simplified relationship here. So within this here, we wanted to find differential equations what the problem asks us to solve for. So we need to solve this for dt over dx. You can see there's our dt and our dx. So we can rearrange and simplify in order to get this in the form of dt over dx. So the first thing I do is I divide both sides over here by this rho VE pi d squared over 4 times our specific heat Cp, which will just leave our dt on this side. So divide that side and this side by the same thing here. And then I can divide the right side by our dx and move it over on this. So we get dt over dx is equal to this relationship here. We can simplify this down and we end up with this expression here that dt over dx, or our differential equation of temperature with respect to distance, is equal to negative pi d times our h bar times the temperature differential of T minus T infinity plus epsilon sigma times T to the 4th minus T surround to the 4th all over this rho VE times our pi d squared over 4 times our specific heat Cp. So this gives us that form there. Now there's a couple things if we look at that we can simplify down a little bit further that will cancel out. So that's our next step in this process for part A here, is to simplify that down. And that's what we have here now. We can see that we have a pi and a d in both the numerator and in the denominator here. So we can see our pi cancels with our pi, our d cancels with the squared from this d here. We can simplify this down here, and then we can move things around and put this up in front here and put this all together. And we end up with dt over dx is equal to negative 4 over rho VE dCp times brackets here h bar times our temperature differential of T minus T infinity minus our epsilon sigma times that temperature difference of T to the 4th minus T surround to the 4th. We're going to call this equation 1. So in part B of the problem, they tell us to neglect radiation. So we can still take this same differential equation, our dt over dx, equal to our negative 4 over rho VE dCp times h bar times our temperature differential minus, now this whole term over here is a radiation term. So this whole term over here can go to 0. So then we're left with just this left-hand side of this, and what we want to do is separate out our variables. So we do this here. We can pull some things out of here. We take our h, pull it out front there, just our temperature differential there. We have this in our denominator. So now from there, what we can do is take this dx on this side and multiply it over to this side. So now we have an expression that says dt is equal to our negative 4h bar times the temperature differential between T minus T infinity all over the denominator of rho VE dCp dx. So from here, we then divide both sides by T minus t infinity. So we divide both sides by t minus t infinity. We get dt over t minus t infinity here is equal to negative 4 h bar over our rho VE dCp times our dx. And now what we can do is we can integrate both sides. So we do integrate on both sides. Limits of integration from Ti, initial temperature to final temperature T of dt over t minus t infinity is equal to, now we can pull out our constants out front, so everything's a constant here except for our dx. So let's pull our constants out times integral from 0 to x of dx. So now that we have our integral set up here, again on the left side we have this integral from t sub I to t of 1 over t minus t infinity when we arrange this times our dt is equal to negative 4 h bar over rho VE dCp, where these are all constants pulled out front of the integral of 0 to x of our dx. So now we can recall the general form here of why we wanted to pull this dt and leave this as 1 over, is we have the general form of 1 over x minus a dx is equal to the natural log of x minus a. So now we can plug in for our specific values into this general form from our table of integrals here, and we end up with, when we take the integral of the left side over here, we end up with the ln of x minus a, or t minus t infinity, evaluated from t sub I to t. Now this is equal to our constants on the right-hand side, our negative 4 h bar over rho VE dCp, times the integral of dx becomes x, evaluated from the limits of integration of 0 to x. So then we come in here, what we can do is we can do out our limits of integration over here, plug in our values, and we end up with the natural log of t minus t infinity minus the natural log of ti minus t infinity there. And now we can recall, if you take the natural log of x over y, you get the natural log of x minus the natural log of y. So we have the right-hand side of this relationship. We can work backwards and put this into the left-hand side here, so this relationship up above now becomes a natural log of t minus t infinity over ti minus t infinity is equal to the right-hand side of our equation over here still, where we have this x that we just put up here, negative 4 h bar x divided by rho VE dCp. So the next step within this here is to rearrange and solve for t. So based off that relationship, we rewrite this now, and we have the natural log of t minus t infinity over t sub I minus t infinity is equal to our negative 4h bar x over rho VE dCp, where the next step we want to take the exponent of both sides to eliminate our natural log. So we take the exponent of this side and the exponent of this side here, we eliminate the natural log there, so we're simply on the left side left with t minus t infinity all over t sub I minus t infinity is equal to, now we took the exponent of this side over here, exp, to the negative 4 h bar x over rho VE dCp. So then what we can do is we can multiply both sides by the denominator here, our ti minus t infinity. We do that there, and we end up with this relationship that t minus t infinity is equal to the exponent of negative 4 h bar x over rho VE dCp times that denominator of ti minus t infinity. Then the next step is to add t sub infinity to both sides, so we end up with now this new equation 2 here, where our temperature T is equal to that surrounding t sub infinity plus this temperature differential of Ti minus T infinity exponent of negative 4 h bar x over rho VE dCp. So now we have this equation here, but we need to find a way to get our h bar. So that's when we take a look at now a relationship shown in equation 7.52 on page 485 of our textbook for a Nusselt number here, average NUD is equal to the average HD over K. So we can take this relationship from equation 7.52 in order to try to get our h bar out of there. So what we realize now from equation 7.52 is that we're going to need a way to find this relationship here. So in order to get this value here, we can use the Churchill-Bernstein correlation, which is equation 7.54 on page 485 of our textbook here, for a circular cylinder and crossflow. And we can use this relationship here. So from equation 7.54, we have that our average NU sub D here is equal to 0.3 plus 0.62 times the Reynolds number to the 1/2 times the PR to the 1/3, all over 1 plus 0.4 over PR to the 2/3 all to the 1/4, times 1 plus our RE sub D times 282,000 to the 5/8 all to the 4/5. Now, what we need to realize here is that in order to use this one, we still need to go to another equation to get our Reynolds number. So we're going to pop over now and take a look at the equation here from page 455 of our textbook here, because we need to get this RE sub D in order to solve for NU sub D over here, average. So we have this relationship here from page 455 of our textbook for Reynolds number here. RE sub D is equal to our rho VD over mu, where this relationship can be simplified down. We can just say VD over our V there, where we have a value here for our V here is 5 meters per second, so D is given to us as 0.005 meters, and our V here is given to us as 3 times 10 to the negative fifth meters squared per second. So we have all the values we need there. It's a straightforward plug and chug to get our Reynolds number. So RE sub D is equal to 5 times our 0.005, all divided by 3 times 10 to the negative fifth. We do our unit analysis, our meters squared, cancel those 2 meters up top, seconds cancel seconds. Unitless, which is what we'd expect, so we get our RE sub D is equal to 883. So now that we have this value, we can go back to equation 7.54. So when we go back to equation 7.54 here, we can plug in now this value of this 883, along with our known value of our PR number, into this above equation here, 7.54. So when we plug this in, there's our 883, there's our PR, there's our 883 there, there's our PR down here, all plugged in where we need them, straight into this equation here. Excel, MATLAB, calculator, whatever you choose, plug this in, and now we can get a value here of 14.4 for our average NU sub D here. So now, after all of that, we go back to the governing equation 7.52 where we started, because now we have a value for this here, and this again was 7.52 on page 485, and now we can solve this for our H bar. Because before we had 2 unknowns, now that we have this from our above equation, 7.54 on our Reynolds equation, now we only have our one unknown of our H value. So rearranging 7.52, solving for our H bar value there. This is equal now. We have the value for our NU sub D average here. And plug this in with our K and our D values, where we have, again, this value here. Average NU sub D is equal to 14.4. Our K was given to us as 0.037 watts per meters times Kelvin. Our diameter is 0.005 meters. Plug those values into this rearranged 7.52. And what we end up with when we do this out is 1.07 watts per meter squared times Kelvin. We do our unit analysis. That checks out for our H bar. Now we can take this value here and plug it back into our equation for temperature. So now going back to our temperature equation here, TO is equal to T sub infinity plus our Ti minus T infinity temperature differential to the exponent of negative 4H bar X all over rho VE dCp. So now we can go back through everything from our first page and everything we've solved for in this, and I want to rewrite what our variables are, what we know, our units, and our values. So T sub infinity was given to us as 25 degrees Celsius, T sub I 600 degrees Celsius. Our H bar we solve for now of 107 in watts per meter squared times Kelvin. Our density rho is equal to 8,900 kilograms per meter cubed. Our V sub E was given to us as 0.2 meters per second. Our diameter given to us is 0.005 meters. Specific heat was given to us as 400 joules per kilogram times Kelvin. Our X for this problem was X is equal to L is equal to 5 meters. So with all these known values, we can plug these back up here into this equation here. So now we have our T sub O is equal to 25 degrees Celsius plus 600 degrees Celsius minus 25 degrees Celsius. And we plug in for T sub I and T sub infinity based off our given values. To the exponent, negative 4. Here's our H bar value there of 107 watts per meter squared times Kelvin, times our X value there, which is 5 meters. Then we have our density down here, 8,900 kilograms per meter squared, times 0.2 meters per second here. Then we have times our diameter here of 0.005 meters, times our specific heat of 400 joules per kilograms per Kelvin. Do out our unit analysis, make sure this works, and we are left with a temperature in degrees Celsius when we plug this in. So T sub O is equal to 340 degrees Celsius. So now for part C, what we want to do is go back up to equation 1, where radiation was included, and solve for T, when X is equal to L is equal to 5 meters. So we go back up to this equation here, so D sub T is equal to our negative 4 over rho VE dCp times our h bar times our temperature differential of T minus T infinity plus our emissivity, because now here's our radiation term here, sigma times T to the fourth minus T surrounding to the fourth dx. So now we have this radiation term in here that we're going to include. So from there, we need to separate variables and integrate. So I made a list of all of our constants. We have a lot of variables in this equation. I need to know exactly which ones are constants that I can pull out before I integrate. So that's the next thing we do is we pull those out. I rearrange this, plug back in, and I have, now that I've moved things around with my variables, this relationship here where I have dt over our h bar times T minus T infinity times our radiation term over here is equal to -4 over rho VE dCp dx. So I move things around just a little bit more, put this 1 over this value here, pull my dt out here just to make it into an integration form that I'm used to solving, and I have this over here stays the same. Next, I need to integrate both sides. So I integrate all of this here, plug in my known constant values. So I'm really just taking the integral of dt over here, which becomes t. These are all constants that come out. Pull my constants up front here, and it's really just the integral of dx. So it's a pretty straightforward integral once I understand which all my constants are. I can pull them out front before I integrate. So I do this out. You can do it by hand, do it in MATLAB, whatever you prefer for a numerical solver. Solve for T. T is then equal to 309 degrees Celsius. So therefore, radiation makes a discernible contribution to cooling the wire when we compare those temperatures.